The broadcast is now starting. All attendees are in listen-only mode.
Okay, good morning, good afternoon. I think for most of you, it's in the afternoon there. So thank you so much for joining. This is Krishna Vidula from the Indo-Universal Collaboration for Engineering Education. And we have with us our very strong platinum sponsor, MathWorks, represented by Dr. Dhruv Chandel, Dr. Spandana Gunaguntla, and Akhil Gopinath. The presentation will be made by Dr. Dhruv Chandel, and we're looking forward to some really exciting information and knowledge to be gained from this webinar on accelerating computations with MATLAB and Simulink. So take it away, Dhruv.
Thanks, Professor Vidula. It's a great pleasure to be here. Good afternoon and good morning, everyone, as the case may be, and welcome to the webinar on accelerating computations with MATLAB and Simulink. I hope I'm audible. If there's any trouble, please post in the chat and my colleagues will be able to alert you. We'll try and fix the issue. So just to give you an outline of what we're going to talk about today, let me ask you a few questions. Maybe your MATLAB code is running quite slowly. Maybe your Simulink models are taking a very, very long time to finish running. And maybe they're fast, but you need results from millions of computations. So in a nutshell, don't fear, we are here to help. So today we'll be talking about how to accelerate your serial MATLAB code, then how to speed up computations using the parallel computing capabilities that come with MATLAB. And finally, if you have access to a cluster or AWS resources, we'll talk about how you can scale up your computations using MATLAB Parallel Server. So it's expected that I'll talk for around 45 minutes or so, and then we'll have some time for Q&A. So thanks everyone for attending. I'll get started now. Okay. So a few points before getting deeper into this. So please be aware that this is an intermediate level session. We will assume some basic knowledge of MATLAB and Simulink. So we assume you know what MATLAB is. Some of you may know what Simulink is. If you want to learn more about this, you can go to the link which is mentioned there, matlabacademy.mathworks.com. We may also use examples from a variety of domains. So please observe the methodology, even if the example is not from your specific area. We do try to keep it as general as possible. So the technique underlying the examples for what you need. And if you want more discussions on your research or teaching, you can email me afterwards. My email is dchandel@mathworks.com. I will share it again after. Great. So the first question is, how can I speed up my serial MATLAB code? Serial means your normal code that you're writing. Okay. First of all, the first thing that I would recommend is, if you happen to be on a campus-wide license or anything similar to that, please use the latest version. Because you might not be aware, but MATLAB code now actually runs almost twice as fast as it did 4 years ago. So if you look back here and look at the MATLAB code in 2015, if you run the same code that you wrote back in 2015 and you run it in the new versions of MATLAB, it's going to be around 2.2 times faster. Why? Because we keep refining the core engine, we keep optimizing the functions and testing them and making sure they're performing as expected. Another tip would be use built-in functions and data types. So these are very extensively documented, and they're well tested with each other, and they're constantly updated. So if possible, you might want to try and avoid the temptation of writing your own code from scratch if there is a built-in function for what you're going to do. I'll illustrate what this means in a second. And finally, functions such as FFT, which is fast Fourier transform, eigenvalues, SVD, sort, etc. These are all multi-threaded by default since 2008. So if you have a multi-core CPU, which you're running MATLAB on, these kinds of functions don't even need parallel computing. They will use all the resources you have by default, or whatever you set them to use, and they will actually run faster than your usual normal MATLAB functions. Okay, so that's one sort of thing. Now, another thing I would recommend before we even move to the parallel computing side of things is that you can try and use more efficient programming practices. So let me talk about what a few of these may look like. First of all, you can try using functions instead of scripts. So functions are little pieces of code that you call from inside a script, and they are generally executed much faster because they don't use global variables. And they're also a very neat way of writing code. So if you can use functions for a number of repeatable tasks, or very frequently used tasks, try and do that. The other thing is, instead of resizing arrays dynamically, you can try to pre-allocate memory. So MATLAB obviously stands for Matrix Laboratory, and most people use it for matrices. And MATLAB is very forgiving in that you don't have to pre-allocate memory all the time. But if you can predict what size your biggest array will be, and you allocate that much memory in the beginning, your code will run a lot faster. We're mentioning this because if you're in this webinar, it probably means you want to speed up your computation, right? The other thing you can do is, instead of reassigning a variable name, lots of us like to reuse our variable names. I'm guilty of that as well. What is recommended is that you create a new variable rather than assigning data of a different type to an existing variable. I'll show you an example of this in a second. Obviously, many of you might be familiar with the capabilities of MATLAB and vectorization. So instead of using for loops, try and use matrix and vector operations which are built into MATLAB if possible, because those are very well optimized by a development team and they will give you much faster results. And a couple more slightly less known things. So avoid printing too much data on the screen. If you have lots and lots of output, then your display driver will actually become the bottleneck of your computation. If you're printing lots and lots of numbers on the screen, your code will run slow. And the other thing is, try avoiding changing directories using cd or add path or rn path when possible, because when you change your directory, your code gets recompiled. So that slows it down. So these are my 6 sort of top pro tips, if you like to call it that, for speeding up your programming in MATLAB. Now let me show you some examples of this. Okay, so let's look at the code on the left-hand side. I hope you're able to read MATLAB code. This is very, very simple stuff. So if I start from the first line at the top here, what I'm declaring is I'm declaring a matrix called A, which has 3 rows. And then what I have to do is I want to double the size of this matrix A, or I may want to do any other computation on it. So the approach that I've chosen is I'm making a for loop, and for every element inside A, I'm assigning a matrix B, which is accessing every single element of A, doubling that, and then putting it back to B. Okay, this is a very common sort of thing that we see people doing. This is not wrong, but it can be done in a more efficient way. We'll show you what that is. The other thing is, maybe you're working with strings. So I put in an example string, a big brown dog jumped over the lazy fox, right? But notice what I've done here. I've recycled that same variable A from up there, and I've assigned the string to this variable. Now what I want to do is I want to count the number of spaces in between the words. So again, I've made another for loop. I've declared some variable count, and I've said, let me run through this entire array, and if there's any spaces in the middle, I'll just increase the value of this number count, and then I'll display this again. Now, this is a very standard way of writing code. There's nothing wrong with it. But if you want to do this for a very huge data set, if you're doing this lots and lots of times, you can consider writing this in a more efficient way. Okay. So the first problem here is that we have a for loop. Second thing is we are using dynamic memory allocation, and we're changing the size of this matrix in every run of the for loop. We are recycling our variable. We are introducing another for loop down there, and we're using an if statement. That's a lot of processing that my MATLAB has to do. So I can rewrite the code as it is shown on the right-hand side there. So if you look at the first line, it's exactly the same variable A. I've just defined it in a more compact way. So if you're making huge matrices, it might be a little bit easier. Now, instead of using that first for loop, I simply write B equals 2 times A. That's a vectorized operation. I don't have to use a for loop. And in one line of code, you can do what these 3 lines of code will do. And you can avoid all of this heavy computation. Okay. Now, instead of recycling my variable A, I make a new variable called S, inside which I put the same string. And then instead of writing my own function or making my own algorithm for counting these spaces, I just use the inbuilt function in MATLAB, which is called ISSpace. And then I add up all the spaces, and that will give me the total number. Now, you might be astonished to find that this very little, almost trivial seeming changes will actually speed up your code by 3 times. This code is not very heavy at all, and still it runs around 3 times faster if you just use the inbuilt functions and the vectorized operations. It's also a lot more compact and a lot more readable to new people. So the key takeaways from your serial MATLAB code would be try and use better programming habits because it will lead to faster code. Try and use vectorized operations where possible instead of loops, and use the built-in functions. So I think most people can sort of figure out how to do this with a little bit of time. Now, the question is, what else can we do? So there are these 2 very famous commands, tick and talk. Maybe you've heard of this. This stands for time in clock and time out clock. So if you write tick and then you write a piece of code, and you write talk at the end of it, it will tell you how long it took to execute that code. I will show you some examples of this later. You can also use MATLAB Profiler to analyze the execution time of each piece of code, and you can see where the bottlenecks are. And you can also load common variables from a file instead of executing a lot of code to generate them repeatedly. So let's say you have 500 lines of code, which is just creating some variables. You don't have to do that each time. Just do it once, save the variables in a file, and next time just load them before doing your computation. So that will help you a lot in terms of being able to run large pieces of code much, much faster. And if you're an advanced user, this is a really special trick or workflow that you can do with MATLAB. So what you can do is you can generate something known as a MEX function, which is a MATLAB executable, and that can transform your existing MATLAB code into C, C++ or CUDA code, and that can be generated from a function. So you can use the MATLAB coder or the GPU coder apps which are provided with MATLAB, and they will generate the code for you automatically. And I should have actually written a bigger number here. So this is, if you're using the right sort of function in C, C++ or CUDA, your processing for certain applications can be actually not 5x, but 500 times faster. Okay, so if you're doing image processing using a GPU, you can use CUDA code. If you're working with hardware at a very low level for very large computations, you should be using C, C++ code. We're not getting into too much detail on that today because it's a slightly advanced topic, but you can reach out to us separately if you want to know more about that. Okay, so far we've talked a little bit about MATLAB. So if you're working on Simulink, there are a few tips for you as well. The first thing you can do is you can try and use accelerator mode. So at the top of your Simulink browser, there's a drop-down menu which says normal, accelerator, rapid accelerator, etc., etc. And what you can do is you can just go from normal mode into accelerator mode. And what this does is it compiles certain parts of your model to C code. And the advantage for this is there are no limitations on the type of model that you can compile. So basically, just before running your Simulink model, it automatically converts certain blocks into C code, and that runs a fair bit faster than your ordinary Simulink models. The trade-off or disadvantage of this is there's a little bit of processing overhead to generate the code, and some of the diagnostic features of Simulink may be disabled. Okay, this is only for Simulink users. We will not spend too much time on this. Another tip is if you're doing very long runs, if you're simulating complex systems, which are running for thousands of seconds or for millions of iterations, you can try using the rapid accelerator mode. So this is very, very good because what it does is it compiles almost your entire model and it makes a standalone executable, and it can run on multiple cores as well. So all the debugging capabilities are disabled in this one, and your whole model needs to be code generatable. But if you're able to do this, you can expect your Simulink models to run very much faster. I'll show you a graph on this because people like pictures a lot. So this blue line here is the normal Simulink mode. The red line is the accelerator mode. And this orange line is the rapid accelerator. Now what we have on the y-axis here is simulation time. This is how long it takes your model to run. And on the x-axis, we have the simulation steps, which is how many time steps we want to run your model for. So if you're doing very short and very easy simulations, let's say, which don't have much computation, you can just go ahead and use the normal mode. But if you're using even a moderately complex problem, you can just try switching to accelerator mode. It will compile certain parts of your model to C. And with just a little bit of initialization overhead, it immediately runs a lot faster. Something like 40% faster than normal simulation. And if you're running really long or really complex simulations, then you can use the rapid accelerator mode. And this will take a lot of time to compile in the beginning. But if your simulations are very long, then this will run faster even than the accelerator. Again, we're not going into too much detail because I guess most of you are here for MATLAB rather than Simulink. But if you have questions, you can reach out to me and discuss it. So just-in-time accelerator is quite fast. Rapid accelerator is the fastest, but it needs some extra overhead. You can also use a facility called fast restart between multiple runs if your model doesn't need to be changed. So it will compile once and then just keep on running. And an additional tip or a pro tip is that you can use reference subsystems instead of different subsystems of the same kind. So if there's a small subsystem which is doing a very common kind of function, you can just use a reference subsystem. It will get compiled once and you can reuse it like normal functions inside MATLAB. Okay, so that's all the depth I'm going into Simulink for now. Now I'll show you what you can do more about parallel. So far we've talked, everything we've talked so far is only about using one core of the computer. That is to say, one CPU core. But your CPU probably has many cores. Probably has something like 2 cores or up to 16 plus cores, all of which is computing power that you can utilize. If you have access to a GPU workstation, you might have hundreds or thousands of cores at your disposal. And if you have a much more powerful workstation or a high performance computing cluster or an Amazon Web Services Elastic Cloud Compute cluster, then you can have thousands of cores of CPUs as well. Okay, so you might have a lot of very powerful hardware which you might be wanting to use for your application. So in that case, what you will need is the parallel computing toolbox for your local machine, or the MATLAB parallel server for your remote clusters or for cloud. And we'll talk about how to use each one. So first of all, what is parallel computing? Now, what we've looked at, all of you must know how to write serial code. It's the first thing we learn in programming. So what serial code is, if you have 4 instructions, all of them will get queued up to this processor and they will get executed one by one. So you queue up one instruction, second one, third one. One by one, they will get into a line or a queue and they'll get executed one by one, and then you get the results in the end. Parallel computing works a little bit differently. So what you're able to do is you're able to send all of your instructions to different CPU cores. So this orange one on the top will go to one core, this green one will go to the second core, this one will go to the third core. And all of these can execute in parallel. And potentially you can get a lot faster computation with your MATLAB or Simulink problems. Why is this useful? Well, I'll give you an example of a kind of problem we used to work on in mechanical and civil engineering. So imagine this is a beam type structure which is made up of lots of little elements, okay, which are all governed by that equation up there. It's okay if you're not from this domain. It's not important that you understand this exact problem. What we're trying to show you is how much faster you can work with them. So if you have one worker in a pool means that's how many processors processor cores you're using. So if you have one processor core and you're computing 25 different values, 25 different values of these variables, it takes around 0.02 seconds. If you're trying to run this for 400 different parameters of these values here, it takes a little bit longer. If you're trying to do 160,000 simulations, it will take over a minute, which is quite a lot of computing time. Now, what you can do is you can get more workers if you have access to a high performance cluster or cloud computing. So let's say you have 20 cores, a CPU with 20 cores. Then all of your computations, especially the larger computations, get speeded up very fast. So instead of taking 70 minutes, this will just 70 seconds, sorry, 70 minutes, excuse me, this will take just 3.6 minutes. If you happen to have 200 cores at your disposal, this will just take a few seconds to execute. The thing to note is your smaller values or smaller number of iterations doesn't benefit from that many cores, because there isn't simply enough work for all of these workers to do. So if you're doing very heavy computing, if you have a lot of extra parameters or simulations that you need to run, then having more workers can be beneficial. And this is sort of the slide that we show for that. So if you have more workers, you can get more and more speed up. And in the case of having 240 workers for a very large number of values, your code might execute almost 200 times faster. Okay. So the more workers you add and the bigger your problem is, the more speed up you can expect out of parallel computing if it is the right sort of problem. And we can look at what the right sort of problems are as well. So typically parallel computing is used for what we call embarrassingly parallel problems. These are problems which can easily be broken down into lots of little ones, which can be solved independently of each other. You might have heard of this term before. It was actually originally coined by Cleve Moeller, who created the first version of MATLAB. So parallel processing is very intimately involved with the development of MATLAB itself. Now, in terms of what kinds of problems can be used or what kinds of problems are embarrassingly parallel, one very good example is mesh-based solutions for ordinary differential equations or partial differential equations. So if you have a big mesh, let's say in a finite element modeling system, or if you're doing heat flow analysis or vibration analysis, you can split up that big problem into lots of little pieces, and you can have different CPU cores solve little parts of that problem. Another thing is, if you're running lots of independent simulations with lots of different parameters, you can simulate each model or each set of parameters on a different CPU core. So instead of doing one simulation at a time, you might do 4 simulations at a time if you have 4 cores. Another kind of problem is discrete Fourier transforms, DFTs. So if you have to calculate the contribution of each harmonic in this, you can do that separately on different cores. This works, I think, quite well with GPUs as well. And of course, one of the most popular examples these days is if you're doing machine learning or deep learning, you might have models of convolutional neural networks, LSTMs, etc., and you train this on a GPU. So what that means is you use each of the cores of the GPU and you solve the entire network with a certain set of parameters, and you basically see how well it performs. So that kind of problem is very much amenable to be solved like that. Okay, so now we know what parallel computing is. We know what kinds of problems are good for parallel computing. The third question is, when should we use parallel computing actually in practice? So the number one question is, do you need to solve large problems faster? If you don't have this issue, then you don't need parallel computing. You can just carry on with whatever you're doing. The next question is, have you already optimized your serial code? So this is the first thing that we discussed, how to write code using inbuilt functions, using vectorized operations, etc. You might be able to speed up your code by 3 to 10 times just by making sure it's written in the right way. And the third thing to consider is, can your problem actually be solved in parallel? Because if it's not an embarrassingly parallel problem, it doesn't matter if you put 1,000 CPU cores inside it, it will not solve any faster. Now, if the answer to all three of these questions is yes, then you need to ask the practical question, do you have access to a multi-core or multi-processor computer? Okay. If you don't have this, then do you have access to a graphics processing unit or a GPU? Or if you don't have either of these two, do you have access to a high-performance cluster or an Amazon Web Services account? So you will need at least one of them to do parallel computing. If you don't have the hardware, then there's not much we can do to accelerate the code. So you have to make sure you have the correct sort of problem and that you have the correct sort of hardware. If both of these sections, the answer is yes, then you can proceed with parallel computing, and it will be useful to you. Just very quickly talking about what toolboxes support parallel computing by default, where you don't even have to write specific code on your own. So if you're using image processing toolbox, let's say for recoloring images or trying to detect edges or anything like that, this contains functions which are hyper-threaded as well as supported by the GPU. So this is very, very easy to use with parallel computing. You don't have to rewrite much of it. If you're using statistics or machine learning with the inbuilt apps, or deep learning with the inbuilt apps, or the inbuilt training methods, you don't have to write your own code. MATLAB knows how to use your existing resources, and it will be able to use it more efficiently. Similarly, for signal processing applications, if you're using FFT filtering or cross correlation or any of those things, you can use your GPU directly for that. Also for computer vision or optimization problems, so this is a gradient estimation optimization problem. Instead of having one worker start at one point and trying to find the value or peak, whatever it is, you can have multiple workers starting at multiple places in the optimization domain, and they can independently try to find out the best possible solution. And there's a link to other toolboxes which are parallel. So you can keep these in mind. These will make it much easier if you're in any of these applications. Okay. So talking about parallel computing, how to actually implement it. So by default, your MATLAB, your software MATLAB copy of MATLAB runs on one CPU core. So even if you have a computer which has 4 cores, by default, your MATLAB instance will run only on one core. The exception to this is some of the functions which I mentioned, FFT, I, STD, sort. These are multi-threaded by default since the last 12 years. So these can work almost automatically with multiple cores. Okay. Now, if you want to run your MATLAB desktop on all 4 cores of your local machine, what you need is the parallel computing toolbox. So what this will be able to do is it will be able to split up your MATLAB code into pieces, which you can run on all 4 cores, and you can use all the processing power at your disposal. And it requires very, very simple modifications to the code. So some of you might have heard of this, but I'll just repeat it here. So if you're using for loops, let's say, if instead of a for loop, you write a par for loop, which is a parallel for loop, your code will start using all the processors that you have in parallel. And we'll talk a little bit about how to do this, what are the good practices. Instead of using the function evaluation feval, you can use par feval. This will be parallel function evaluations. And also, instead of sim, you can use par sim. So this will run your Simulink models in parallel, and you can speed it up that way. All right. I think I'm running a little bit behind time, so I'll speed it up a little bit. Okay. So how does par for work? This is the parallel for loop. So by default, when you run a for loop and you have 5 pieces of code that you need to execute, or 1 piece of code that you need to execute 5 times rather, if you replace this with a par for, what will happen is each of these tasks will independently go to different CPU cores, and these will get executed independently. So if you want to do things like parameter sweeps or Monte Carlo simulations or anything like that, which are independent tasks, you can very easily use a power for loop for that. So let's show an example of how that works. Let's say I call some function a of I, and I use a power for loop for this. So what this will do is it will create 10 tasks from 1 to 10. And instead of processing these one by one, it will actually break up these tasks into certain packets and send them to the workers. So tasks number 1 and 2 go to this one, 3 and 4 here, 5 and 6 here, 7 here. Now, after a task is complete and that worker is free, the next task from the queue will get assigned to this one. And so on and so forth until all the tasks are finished. And in the end, all the variables are returned as the output. So the key thing to understand here is that using parallel computing does not require you to modify your code a lot. You just have to make this one change. If your tasks are independent, it just works like this. It's very, very easy to use. So if you were to write, let's say, a for loop which runs from 1 to 10, you pause it for 1 second and you just display the value in the for loop. I'm using tick and tock commands to time this execution. What happens is your for loop will spit out these numbers 1, 2, 3, 4, 5, 6, 7, 8 in series, and it will take just over 10 seconds to do it. The same thing if you repeat that using a par for loop and you time it using tick and tock, what will happen is all these tasks will go to different CPU workers, and they will get executed out of order. So it's 1, 5, 2, 3, 8, 4, 6, 7, 10, 9. This sequence doesn't make any sense, but as long as the tasks are independent, the par for will be able to run it much faster. So this executes in around 3.5 seconds. This was with 4 workers, I think. So par for has a little bit of overhead because it has to open the pool and exchange the data with the workers, but it can still speed up your computation by a lot. Just by replacing this for with a par for, you get 3 times faster. Okay, so let me show you an example. This is what is called as a Van der Waals equation. I won't explain the equation now because there isn't time. What we're trying to do is do a parameter sweep. So we're trying to plot different values for around, I think, 36 parameters or something close to that. It's probably 30 parameters. Now, what happens is with a for loop, these values are generated one at a time. So you can see the computation is happening, a new value is generated, the graph is updated, and so on and so forth until the computation is finished. This looks like probably 20 values. Okay. If we see how long that kind of computation takes, it's around 38 seconds. Now, instead of using a for loop here in line 15, I just use a par for loop. And what you can see are multiple points are being added to the graph at the same time, simultaneously. And this takes 1/4 of the time because I was using around 4 processors. Let me repeat this video from halfway through again. So in line 15, I changed the for with a par for. If you pay attention to the graph on the right-hand side, you can see multiple points are being added simultaneously because 4 processors are trying to solve the same problem and they can do it 4 times faster. So that's one way of using a par for. Some factors that govern the speed up. If the computation time is too short, then par for will not be much use. Execution might be slow if you're trying to run, if you're running out of memory or if there are file access limitations. If your hard drive is too slow, then your CPU being faster will not matter. And certain functions are multi-threaded by default. So if you use those in parallel, it won't make any difference, like the FFP, sort, I, etc. And there might be unbalanced load as well. So if you're running very long simulations on one CPU and short simulations on the other CPU, par for may not be very helpful. Okay. Very quickly, I'll show you what you can do. You can do the same thing with Simulink. So many of you might be working in research applications where you have complex Simulink models, and you're running these models for hundreds or thousands of times to try and get some values out of that model. So this is a very simple model that I'm running right now. It's just going to be an ordinary differential equation, mass spring damper system. And you have to change the value of the mass, keep the value of mass fixed, change the damping and spring coefficient, and try to understand the behavior of this system when you're changing some parameters. So you can call Simulink models from MATLAB by using the sim command. I'm sure at least some of you must be aware of this. If you use the parsim command for parallel simulations, let me show you what that looks like. And the speed up is really impressive. So first, talking about how the model is set up. This is a mass spring damper system. And we're going to sweep through the, I think in this case, I'm sweeping through the frequency values because I'm exciting the mass spring damper signal with the sinusoidal input. The model looks very, very standard. It will open in a second. I'll show you what it looks like. So this is your normal mass spring damper model. I'm just taking the maximum values of displacement and velocity outside. And the sinusoidal input that is going to the model, I'm just changing the frequency to see what effect it has on my simulation. So if you're working as a mechanical or civil engineer, this is a very standard thing. Now, the way you set up a parsim is that you have to use the special construct, which is simulation input, and you have to set the parameters of the block using a formula. So this is just a setup step. You have to do this once. If you're interested in the code, I can share this with you afterwards. After we set up the frequency sweep, we use the parsim command from inside MATLAB, line 27. What this will do is this will open up the parallel pool of workers. And then without having to compile the Simulink model again and again, it will call it again and again with the same with different parameters. So you'll see the speed of the execution in a second. So it loads the model on the parallel workers. I have 4 workers, I think, on this machine. And within the space of around 3 to 4 seconds, it's able to run a Simulink model around 50 times. Normally, if you use Simulink, you click on that green button, it compiles, it takes a few seconds to run. If you had to do 50 things manually, it would take a long time. But if you run it in this way, you can generate results which would take you around a week to generate manually within probably a few minutes. I've used this in my PhD, so I can claim that with some confidence. And then you can plot the outputs and you can do whatever you see. Okay. So in summary, getting the most out of MATLAB on a single machine. First of all, use the latest version. Follow the best practices of programming. You can use the implicit multi-threading in some of the inbuilt functions, or you can use the multi-threaded MATLAB workers in the tab for thing. Here. Use GPU on how you accelerate code using GPUs. It's a very similar process. Instead of making a normal array, you make a GPU array, and all the execution is done on your GPU. What I want to do now in the short time I have left is just talk about scaling up MATLAB. So, MATLAB runs on your desktop PC, which probably looks something like this. If you want to use multiple processor cores or GPU, but if you want to really scale it up, solve very complex problems on HPC clusters or Amazon Web Services clusters, what you have to use is the MATLAB parallel server. So this is a separate product, but if you're on the campus-wide license, it probably comes bundled with whatever you've got. And what this is able to do is, this is able to scale up your computation to hundreds of workers. And it comes with a built-in job scheduler, so you can submit jobs interactively and you can offload the computations to a big cluster and then you can get the results back. So I'll show you one method of doing that today. So the idea behind using MATLAB parallel server is you can prototype your algorithms on the desktop. So maybe you use let's say 5x5 grid of parameter sweeps. You perfect or optimize the algorithm on your desktop machine. Then you send it to the parallel server and do a 1000x1000 parameter sweep here. So all of the development, which is sort of the easy thing to do in MATLAB, you do it on your normal machine, which you're familiar with. And all of the heavy computation, you shift it this way. So you get the best of both worlds. You get the easy user interface and development of the MATLAB environment, and you get the processing power of the big cluster. And these work together very nicely if you have the MATLAB job scheduler, which comes with the MATLAB parallel. Okay, another thing which is being very, very popular these days is that if you have an Amazon Web Services account, you can use the EC2 facility, which is the Elastic Cloud Compute. And what this allows you to do is it will allow you to make your custom high performance cluster very, very quickly for on-demand usage. And this is very inexpensive compared to conventional HPC setups because you don't have to pay for a cluster. You don't have to have space or electricity or cooling or any of that stuff. Amazon handles all of that. What you do is you just make an account. You purchase whatever package you like, and then you can get whatever size cluster you want online. You can make it and you can delete it also. It takes around 10 minutes once your Amazon account is in place. So what you have to do to get access to that is you have to go to MathWorks Cloud Center. This is cloudcenter.mathworks.com. You go to create a cluster, put a name on your cluster, select the configuration. So I'm selecting a 4x8x large machine, which has 18 cores. And then you just click on start. So if you have an AWS account set up, this entire process takes around 10 minutes. And in 10 minutes, you have access to your very own high performance cluster, which you can use and then release. And you pay as much as you use. So the way it works is inside your MATLAB window, there's this option parallel. If you click on that and then you go to discover clusters, you can add whatever cluster you created in here. And then you have to select your default profile. So you change it from local to the cloud cluster profile. And this is set up automatically if you do the discover cluster option. So first of all, go to parallel and then discover clusters. Change the hardware. So just replace local, which is your local machine, with the name of your profile. So that might be the cloud cluster. And you can also do this programmatically. So instead of local, you choose whatever new cluster you've made. And your parallel pools or your jobs will be sent to that big cluster you just got access to. To show you an example of how fast and effective this is, I'll give a slide a moment to load up. So what I've got here is I'm running that Van der Waals equation that I showed you just now. I think it's 1000x1000 grid, and we're running it with 1000 workers. So if my desktop MATLAB has 20 workers, my local HPC cluster has 200 workers. My local cluster has 200 workers in the lab, and the HPC cluster has 1000 workers. What you can do is you can scale up the computation and have all the processors solving the problem in parallel. So if I run this again, you'll be able to see that that HPC cluster with 1000 workers can solve many, many points at the same time, simultaneously. While your desktop is only just getting started and your 200 workers are very, very slowly populating these environments. And the computation might take a couple of minutes with 1000 workers, which would take you probably several hours on your desktop. So this is one of the reasons to scale up your big cluster. if you're solving a time-bound problem, let's say you're working on something very cutting edge, it has to be delivered quickly. You don't have that much time to waste. Maybe you have to finish your PhD, or maybe you just want to get your work done fast because your time is valuable. All of us are busy people. So what you can do is you can get access to more workers and you can finish your job much more quickly. You can try out different algorithms and get better results. Okay, I think my time's almost up, so I'm going to skip this last part. This is about batch jobs, how to submit jobs. Not really important right now. We can talk about this afterwards if someone has issues. So in summary, if you want to accelerate your MATLAB and Simulink computations, first thing is optimize your serial code, get the latest version, use the built-in functions. If you have a desktop machine with multiple CPU cores, you can use PowerFor, PowerFeval, and PowerSim to use the full capacity of your computer. And if you have access to a cluster or a cloud, then you can use MATLAB Parallel Server to really go big and have access to thousands of cores for solving really big jobs. Okay, so I think that's mostly it for my presentation. I would request you to please fill out the survey form. My colleagues will be able to put in the link in the chat window. And I think we'll have 15 minutes for questions now. If you have a private question, you can email it to me. My email address is there.
Okay, great. Dr. Dhruv Chandal, fantastic presentation. And Spandana has been responding to some of the questions already. So let's get some more questions in there. And I think Dr. Spandana can also read them.
Spandana, anything we should answer? Any question you may have missed?
Let's see. So she has sent the link, I think, to the survey. Oh, so she can unmute herself. Yes, Spandana, go ahead. Yeah.
Hi, Dhruv. We have a number of questions. I have answered some of them here. So mostly the questions are about Simulink and how simulation time can be made faster in Simulink. So could you elaborate a bit about PowerSim and how it can be used?
Right, okay. That's a very good question. And I'm very pleased to have gotten that question because most people don't answer about Simulink that much. Okay, so let me actually try and open Simulink. I hope you can still see the screen. So I'll just open a blank model to show you where the option is if it loads up quickly enough. It's taking a little bit of time. Let me just talk about it first. Okay, so there are multiple modes you can use in Simulink. There is the accelerator mode, which uses JIT compilation to generate C code for certain parts of the model. So that has a relatively small overhead, but it can lead to faster runs just out of the box for any kind of model. And for very long runs, you can try the rapid accelerator mode, which compiles the entire thing to code, but then you lose all of the debugging capabilities and basically everything except for the scopes and viewers. Let's say. So this is the sort of graph that we have of the speedups. So your normal Simulink model takes, let's say, 1 second to compile, and then it runs normally in this blue line. Now, what the accelerator mode can do is it takes a little bit more time to compile in the beginning because it can convert certain blocks to C code. But after that initial little bit of investment and overhead, then it runs a lot faster for subsequent simulation steps. So if you're doing long simulations for hundreds of seconds or with very small time steps, then the accelerator mode might be able to help. It works even faster if you enable the fast restart option. So between multiple runs, it does not have to compile again and again. You compile it once and then you just feed it different parameters. The other thing is the rapid accelerator mode. So for that one, you compile the whole model, basically the code, but the overhead is quite large. So this you would use if it's a very long simulation, thousands of seconds or something. Let me try and see if I can open Simulink now. I don't know why these options are grayed out. Let me make a very simple one.
So lots of questions are coming in. Let them come in. I think we can always, Sridhar can always compile them and send them over to both of you. And you can respond to them one-on-one later on, but go ahead, yeah.
Okay, I think we have 10 minutes if I'm not wrong.
Yeah, sure. Go ahead, yeah, keep going, yeah.
Thank you. So up here, you can see in the Simulink window, you can use the normal mode or the accelerator mode or the rapid accelerator mode. So I've told you what these do and what the advantages are. And you can also enable the fast restart. So if you're not changing any of the parameters inside the simulation, this fast restart will prevent you from having to compile the model over and over. It will basically just run whatever was compiled. So I hope that helps. I'll quickly talk about parsim and then get to the next question. So where was my thing? Okay. So the way you use parsim is you actually have to call Simulink from inside MATLAB to make the model, and you choose any one or two parameters that you want to vary. After that, you have to use this command, simulink.simulation input of your model, and then you have to set the block parameters using a for loop. So let's say I'm using lots of different frequencies. In a particular for loop, I will just go and set the different frequencies for each of the different simulation modes. After that, when I use the parsim command, it's actually able to compile the Simulink model almost like a function, and then it just runs it with the different parameters, and you get extremely fast simulation runs. Like you can see, it runs 50 times in probably less than a couple of seconds. I'll try to show you the documentation page for this. So if you go into MATLAB and type doc parsim, and then click on examples. Oops, examples. Oh, there it is. Okay. So parallel simulations using parsim, parameter sweep, and normal mode. So you can get the examples from the documentation as well. If you can't find it, just email me. I'll send something to you. So you can do this using rapid accelerator as well. Okay, Spandana, could you please guide me to the next question? I'm not sure.
Yes, Dhruv, but participants, before we continue the Q&A, just a reminder, please fill in the survey form. I have pasted the link in the chat window. If not, you can type http://tiny.cc/parallel computing with P and C are capitalized. So the link is in the chat window. Please click on the link and fill in the survey. I'll walk through the remaining questions. One more question we have, Dhruv, is there a TikTok equivalent for computing how much time simulation takes?
Sorry, your voice dropped out completely. Could you please repeat that?
Dhruv, can you hear me now?
Yes, yes.
There is a question that asks, is there a TikTok equivalent for Simulink?
Good question. I'll have to look it up. I think you can use the Simulink profiler most likely. So to draw Simulink profiler. I tend not to use this too much. Yeah, so the Simulink profiler is there. You can go to debug and then performance advisor and then Simulink profiler. And you can run your model and it will tell you which pieces are causing the slowdown basically. So what you have to type in the window is doc Simulink profiler. This is probably the best thing. Otherwise, you can use TikTok from within MATLAB and just use the same command. Could we have the next question, please?
Yes, just give me a moment while I share the feedback link to all these participants who are asking again. So someone asked, why does JIT compilation, why is it faster compared to say standard MATLAB execution? Why is a MEX core, why does it run faster?
That's for MATLAB code, not Simulink.
Yes, you're right, for MATLAB, for Simulink, for MATLAB, that is.
For MATLAB, okay. So yeah, I mean, basically it's not just in time in that case. You have to go to apps up here, and then you have to go here into code generation apps. And then from here, you can generate code for C, C++, or GPU, or the GPU CUDA is basically CUDA code. And what you typically do is, I mean, I can show you an example of this. Let's find it very quickly. I have a code generation example. So right. So if you have a problem which is something like this, it's an image processing problem. Either you can use MATLAB code to try and figure out where all these green circles are, or you can pass this image to a compiled C code, which can do the same task for you. Okay. So what you do in that case is you basically can, whatever function you have for creating this mask, I have this particular kind of function here, which generates the green mask for that image based on some color threshold. What I can do is I can go and generate code using the inbuilt coder. So I can say coder.config next, enable or disable certain flags, and then I can pass that function create mask to my code generation function. If I run this, it will do it in a second. It's a couple of seconds. So you only have to do this once. Once you manage to prototype your algorithm in MATLAB and you've got it working properly, you can generate the code. And then after that, it will give you a file that looks like this. So if this was my MATLAB function, create mask, the C function will look like this, create mask underscore mex w64. This is Windows 64. When I run this a couple of times, you'll see I start getting speed ups. So the time it takes for MATLAB to execute versus for the C function to execute the next function, it's around 6 times faster because this code has been compiled. So that's why compiled code actually runs a lot faster, but it only works for certain kinds of applications. So this is a slightly advanced topic. You can reach out to us, Spandana or myself, and we'll be happy to help out with this. So you can do this both for C, C++ code as well as CUDA code. HDL code I'm not too familiar with, but that's also possible.
One more question we have is there a difference between embedded coder and MATLAB coder?
Good question again. So I think the embedded coder relies on the MATLAB coder. So what happens is if you take a MATLAB function here, this function, if you generate C++ code out of this or C code out of this, it will be generic C code. So what that means is, that will be C code that can be used anywhere, right? What the embedded coder does is it generates code which is specifically tuned to run on a particular kind of processor. So the C code that will be generated out of this function, for example, if I want to run this on a Raspberry Pi, that C code will be optimized for the hardware of the Raspberry Pi, which means it will have the same limits on memory and things like that. So embedded coder needs MATLAB coder to function, and it's one step deeper, if it makes sense. So your embedded coder will use MATLAB coder, and then it will make its own refinements based on the hardware you're trying to run. And if you want to get the hardware support packages, you can go to Home, Add-ons, and then get hardware support packages. That's where you can get the MATLAB support for Arduino, Raspberry Pi, or any of those things. Last question, maybe?
That's all. I don't think we have many other questions. Okay, one more question we have. Can Fortran programs be programmed in MATLAB with parallel processing?
I would say tentatively yes, because I've done it myself. So what you need to do is make something which is known as a wrapper. Let me try and show you. So MATLAB Fortran interface. Okay, I mean, this is probably not the answer here, but what you have to do is you have to make a wrapper which can get the data of your Fortran code into MATLAB code and vice versa. If that Fortran code runs on one processor, then you should be able to use Power4 to run it on multiple processors. So I have done this successfully during my PhD time, but it depends on what Fortran function you have. If you do everything in MATLAB, obviously that's much easier.
Okay, since the time is up, what we should do is we have a few more questions, but I think Sridhar, if you can put all them together in the report and send it over to Anand, and then maybe they can respond to them by email. And also, link will recording will be prepared and sent over to you, so you can share it with anybody you wish. So I think with that, let us call it quits right now. And thank you very much, Dr. Dhruv Chandel and Dr. Spandana, and of course Anand, for this very enlightening webinar on how to speed up things with MATLAB. We still have about 400 people still with us, which shows there's a significant level of interest here, and there are several questions which need to be answered. So thank you so much, and appreciate your help, Dhruv and Spandana.
Thank you very much, sir, for organizing this. Thank you.
Thank you.
Thank you, sir.